Well, there are universally agreed that there's two texts you can read on this subject. They're both by me. There's a black one and the blue one. And you should all buy at least 2 copies of these. One for yourself and one to give to your parents for Christmas. And if you download them from an illegal Russian website, then a bear will come around the corner and eat you up. If you're only going to buy one, then buy the blue one because it's a nicer colour. This is also a graduate textbook, whereas this is more of a monograph. As I gather you all come from rather diverse backgrounds, I thought I'd start at a fairly basic level, talking about manifolds and vector bundles, but hopefully we'll get a little bit more advanced in a couple of lectures. So I do encourage questions, both during the lectures and there's going to be a question and answer sessions later on, I think. But we'll start with section 1 on differential geometry background. So the topics I'm planning to cover are vector bundles, connections on vector bundles, and curvature, and then Riemannian metrics, Riemannian curvature, the Leibniz connection, that kind of thing. So let's start off with the section 1.1 on manifolds and vector bundles. So I think I want to assume that basically you've all done some basic course in differential geometry, but just to remind you, we will be discussing smooth manifolds, so I'm going to write my manifolds usually as X, where X is basically a topological space. Which has to satisfy the global conditions of being Hausdorff and second countable. Sometimes people assume paracompact instead of second countable, but it doesn't make a lot of difference. This is equipped with an atlas. So let's write that. Curly A. I usually write my atlases as a set of pairs ui phi I for little I in big I. So this is an indexing set. So then the ui and phi I are charts. So ui is contained in R to the n, is an open set where n is some fixed dimension of our manifold X, and phi I has to go from ui into X, is a continuous map and it's a homeomorphism, meaning an isomorphism of open sets with an open set, the image of phi I contained in X. So that's what a chart means, and you have the union over all little I and big I, the image of phi I is X. So the charts cover X and two pairs ui phi I uj phi j are pairwise compatible. Meaning that phi j of phi inverse is smooth on its domain. And the smooth inverse for all little I, little j, and big I. Okay, and we'll also be talking about smooth maps f going from x into y, smooth maps between manifolds. Okay, so this is all very basic. Next, let's talk about vector bundles. So, a vector bundle E over X. So X is our base manifold. So this is a smooth manifold E. So let's say of rank k. So that's a dimension really. K is 0, 1, and so on. A natural number. So it's a smooth manifold E and a smooth map. Let's call it pi, going from E into X. And that's not all of the structure yet. And so the rest of the structure is that for each point little x, in big X, we are given the structure of a real vector space on the fibre E little x, which is pi inverse of little x, and this is for all, or for each little x in big X. So for each point x in the base big X, we have you can think about E as being like this. Maybe E is two-dimensional, X is one-dimensional. And the projection is mapping things down. We don't do colours here, okay. And then for each point little x, the fibre E little x is the part of E lying above X. So each fibre is given the structure of a vector space, which is in fact going to be finite dimensional vector space of dimension k, but that will come out of the this condition in a moment. So the condition is such that for all, well, every little x in big X has an open neighbourhood U in X containing little x, and a homeomorphism, no, let's say a diffeomorphism between pi inverse of U, which is an open subset of E, and U cross R to the k, where k was the rank of our vector bundle, such that well, if we draw ourselves a square, So u is on the bottom. Up here we have pi inverse of u, which is the open subset of v. And over here we have u cross r to the k. There's an identification here, a diffeomorphism of smooth manifolds. And this square commutes. This square commutes. And once we know that, we can identify let's say E little y with the point y cross r to the k for little y in u. So once we know that this square commutes, we know that for each point little y in u, the fibre EY up here gets identified with the point y across r to the k. This should identify the vector space structures. On the fibre E at y and y cross r to the k, which is just isomorphic to r to the k with its usual vector space structure. So this definition is a way of saying that, well, we give each fibre Ex a structure of a vector space. We want these structures to vary smoothly and trivially, and locally trivially over the base. Okay, so that's the formal definition of a vector space. Okay, so, well, important examples. Vector bundles are the tangent bundle Tx, cotangent bundle T star of x, and the tensor bundles big tensor to the k, Tx, tensored with big tensor to the L, T star of x, and so on. So in my lectures, I'm only really going to be interested in the vector bundle being the tangent bundle or one of these associated bundles here. So UG, I think, will be talking about manifolds together with a vector bundle which is not really attached to the manifold at all, it's just some extra data. Okay, so a section S of a vector bundle E over x is a smooth map little s going from x into E, such that pi composed with s is the identity map on x, which is the same as saying that s at the point x lies in the fibre E at x for each little x in big X. So in a picture, if this is E upping down to x, then S is some kind of it's a choice of element of the fibre for each point little x, big X, and because we're working with manifolds, we can require this to be a smooth map, which means that these points S of x vary smoothly with the base point x. They're not merely continuous or arbitrary. And then S of x varies smoothly with x, little x, which means that we're going to be able to talk about differentiating sections. So just as an example, so a vector field is a section S of Tx. So I'm going to use the notation S lies in gamma of Tx. So big gamma of a vector bundle means the sections of the vector bundle, a set of sections, and in fact it's a real vector space. So if you want to think about this visually, then a vector field is kind of the set of arrows on your manifold pointing in some direction. So you can think of a vector field as the velocity of a fluid in motion on x. So if, for example, your manifold is the surface of the Earth, that would be a two-dimensional manifold, then the wind speed and velocity and direction gives you a vector field on your manifold X. So everywhere the wind is pointing in some direction. If you've got, you can also follow the, if you start at a point, you can follow the fluid flow. So starting at a point, you can look at the kind of, you can solve an ODE for the motion of a point moving along a vector field, and that's going to be important later. Okay, so if f going from x into r is a smooth map, and v is, well before that, then, well, we have the derivative df. So this is basically all the partial derivatives of the function in the coordinate directions, but globally this is a smooth section of the cotangent bundle, and if v is a vector field on x, then okay, curly LV of f, which is v dotted with df. So this is now a function on f. So the notation LV is the Lie derivative in direction v. So here we've got a vector field which lives in Tx, df lives in T star of x, which are dual vector bundles, and the dot here means that we pair the Tx with the T star of x to give you a number or a function. So this is the derivative of f in direction v. Okay. Right, so far so good. Now, next I want to start talking about connections. So connections are going to be very important both for the subject of holonomy groups and also for Yuji's lectures about gauge theory, because Yuji will basically be talking about connections on vector bundles satisfying some curvature conditions and moduli spaces, so families of such things. Let's have a section 1.2 about connections on vector bundles. So let's suppose that we have E over X is a vector bundle. And you have some section S in the sections of E is a section. So, manifolds are basically kind of a general class of spaces on which you can do calculus, what you can do differentiation and integration. So, and that's why we have smooth manifolds rather than topological manifolds. So, what we need to understand now is what does it mean to differentiate a section of E. So, what would it mean to differentiate S? Okay, well, so you can try and write down what you think the derivative would be. And we need to differentiate S in some direction. So let's give ourselves a vector field. Well, if V is a vector field on X, we could try to define the derivative, or L, no, let's not write Lie derivatives, let's write some kind of partial derivative of S in the direction V is equal to, and let's write quotes there because the right hand side is not actually going to make sense, the limit as epsilon goes to 0 of S at the point, let's say this is at some point little x, S at the point x plus epsilon V minus S at the point x all over epsilon. Okay, so that's, we're taking the definition of differentiating a function and we're trying to apply it in this context. So here what I mean by x plus epsilon V is the point which you get by starting at the point x and then moving along the vector field V for time epsilon. This is just another point in the manifold X. So if S were a function, this would actually be well defined. Okay, but it's not. Okay, so, but this is not well defined. Because, well, the two things S at X plus epsilon V and S at X lie in two different vector spaces. they lie in the vector space E at the point x plus epsilon of v, and E at the point x. So if they were the same vector space, or if we could identify those vector spaces, then we could define the derivative. So so to make this well defined, we need some extra data. The extra data is called a connection on our vector bundle E. So a way of thinking about what E does, it's going to be, we're going to write it nabla, which is a kind of upside down triangle. This is actually a Egyptian character, I believe. A connection nabla on E, and so then roughly what the job that nabla does is that nabla identifies the fibers E at x and E at y when x and y are when they're kind of close in x, and you might want to say infinitesimally close. So if x and y are 2 points in your manifold which are very close together, then the connection identifies the fibers of the points there, and then we can think about S here and here as living in the same vector space, then we can subtract them and take a limit. Okay, but that's not the actual definition of a connection. So there are several ways of defining a connection. Let me give you one. So make a definition. A connection nabla on E is an R linear map nabla going from the sections of E into the sections of E tensored with T star of x, satisfying a bunch of conditions. Okay, so here E is a real vector bundle. E tensored with T star of x is also a real vector bundle. So basically, algebraic operations you can do to vector spaces, you can also do to vector bundles over a fixed manifold. So you know about the tensor product of vector spaces. You can also tensor together vector bundles on the same manifold, and then you get another vector bundle on that manifold. The sections of E, this is the set of all smooth sections of E, which is a real vector space, because you can add together sections, you can multiply sections by a real number, you get another section. So I want a map between these two infinite dimensional vector spaces, which has to be real linear, so it preserves addition, it preserves scalar multiplication, and it has to satisfy the conditions so I want it basically to satisfy the product rule. So I want to take the derivative of f times s. So f is going to be a smooth real function. S is going to be a section of E. This has to be f times the derivative of s plus s tensored with d of f. So that you can think of as the product rule for differentiation. It also gets called a Leibniz rule, and this is for all smooth functions f going from x into the reals, and all smooth sections S in the sections of E. Okay, so here df is the derivative of f, which we suppose we already understand. We already know how to differentiate smooth functions, so we're going from knowing how to differentiate smooth functions to knowing how to differentiate sections of vector bundles. So df is a section of t star of s here, so therefore s tensor ds is a section of E tensor t star of x. So this is telling you, and this just says, well, you differentiate s and then you multiply it by the function f, and so in fact gamma of E is not just a real vector space, it's also a module over the algebra of smooth functions on the manifold x. That is, you're allowed to multiply sections of E by functions, and you're allowed to multiply a section of that by functions too. Okay, and so we also write nabla in the direction of a vector field V of S is equal to V dotted with nabla of S for V, a vector field on big X, where here V is a section of T of X, nabla of S is a section of E tensored with T star of X. And by this dot here, I mean that we use the dual pairing, which basically maps Tx cross T star of X into R to contract together that factor and that factor to end up just in E. So then nabla V of S is the derivative of S in the direction V. Okay, so so that's the definition of a connection. There's various other ways of writing it. We should know that connections exist on any vector bundle, but they're non-unique. Well, unless your manifold or your vector space have dimension 0. So there, and there's usually, well, unless you've got some extra data, there's no way of choosing a natural one. So they form an infinite dimensional affine space modelled on the infinite dimensional vector space, the sections of end of E, which is just E tensor E star, tensored with the cotangent bundle of X. So the sections of this smooth sections of that vector bundle is an infinite dimensional vector space. The set of connections is an affine space, which means it looks like this, but there's no natural choice of origin, really. Okay, so that's all a bit abstract. It might help to think about what connections look like in coordinates. So if you want to do coordinates for manifolds and vector bundles, what you want to do is to first choose a coordinate chart on the manifold X itself, and then choose a basis of sections of the vector bundle E over that open set. So we can write nabla locally, meaning just on some sufficiently small open set in the manifold X in coordinates as follows. Well, firstly we choose some smooth coordinates x1 up to xn on an open set U contained in X. So the upper numbers here, they're just indices, they're not powers. For the tensor notation on manifolds, it's conventional to put the index of coordinates upstairs because it fits well with the kind of usual index notation for tensors. And then we also choose a basis of sections let's say E1 up to EK. So I'm going to write these things as xi's and these things as E alphas. So I'm going to use Roman indices for the coordinate indices, Greek indices for the section, the vector bundle indices, for E on U. So you can only choose a base of sections like this if the vector bundle is trivial, but by the definition of vector bundle, it's always trivial on small enough open set. So if you use a small open set in X, just a ball around a point, let's say, then the vector bundle is trivial on that ball, and we can choose a basis of sections of it. So then we can write the derivative of sum from alpha is 1 up to k of f lower alpha e upper alpha is equal to the sum over all alpha is 1 up to k. So k is the rank of my vector bundle, and I is 1 up to n, where n is the dimension of the manifold X. It's the sum of partial f alpha partial x upper I times e alpha tensor dx I. So this is the obvious thing you'd write down if you're trying to differentiate this thing. But you need to include whatever contributions from the derivatives of the E alphas as well as the derivatives of the functions F alpha. So plus the sum over all alpha and beta is 1 up to k, and I is 1 up to n of gamma alpha beta I times F alpha times E beta times tensored with dx upper I. And this would be true for smooth functions f alpha going from U into R. Well, so this has to be true for all smooth functions F alphas, and for some smooth functions gamma alpha beta I going from U into R. Okay, so the gamma alpha betas, that's a kind of coordinate representation of your connection. And that's the kind of free data in the connection. So locally at least, any smooth functions, gamma alpha beta I, give you a connection. This is a kind of the general form of something satisfying this Leibniz rule, this product rule here. In fact, it's not difficult to show that once you've trivialized your vector bundle and coordinates, then a map nabla satisfies this condition for all f and s, if and only if it is of this form for some gammas. Okay, so the gamma alpha beta I are called Christoffel symbols. And you can define them by, if you take the derivative of E alpha, this is on U, this is a sum over all beta is 1 up to k, and I is 1 up to n of gamma upper alpha lower beta I times E beta tensor dxi. Okay, so if you're familiar with the tensor index for notation, the index notation for tensors, you tend to have upper indices and lower indices. In this case, I've got two vector bundles going on. I've got my vector bundle E, and I've also got the cotangent bundle T star of x. So the I is a T star of x index. The alpha and the beta are both E indices, but the alpha is basically E, the beta is the dual E star. So later on I'm going to fix my vector bundle to be the tangent bundle, and then I'll use all Roman indices rather than having Greek indices for E's and Roman indices for tangent bundle indices. Now these Christoffel indices, they look as though they're some kind of tensor, but technically they're not a tensor. And the important thing about tensors is that, okay, so once you choose a coordinate system, then you get some kind of generalized matrix of functions. But then if you change coordinates, that generalized matrix of functions is supposed to change by kind of matrix multiplication of each index by the dx by dy, kind of the Jacobian of the change of coordinates. But these things don't have that transformation law when you change coordinates. They have that transformation law plus some kind of extra term involving second derivatives of one coordinates with respect to the other, or one base of sections with respect to the other. So it's kind of important that these guys are not actually a tensor. And for that reason, setting gamma equals 0 is not a natural choice, because gamma equals 0 in one coordinate system, or one set of trivialization of E, would not correspond to gamma equals 0 for a different set of coordinates. Okay. Any questions at this point? No? Okay, so I think we probably have a break now, but I've then forgotten what the next time is.